Today we're going to talk about preventing myopia, at least one theoretical way that might happen. And we're going to talk about first how this might happen, and then we're going to go over an article that tests the whether this outdoor activity is actually protective or not. And first, let's talk about anatomy. You've just been studying that. And you know that we have three cones, different types of cones and rods. And the central focus is mostly red and green, and the periphery is red, green, and blue. Most of the research in myopia control and myopia in general has focused on the periphery because it has all three of these cones, whereas the central only has red and green. Now, there's an interesting thing that the wavelengths, the visible light spectrum, is about 350 to 750 nanometers, and it's actually about 1.75 or 8 diopters wide, and the retina isn't that wide, so the whole visible spectrum can't be in perfect focus at one time. Blue tends to pile up at the low end, rod's kind of in the middle, and green, and then red. And so based on where they fall on the spectrum, they're actually firing at different rates. To support this, there are many electroretinogram studies that show that an electroretinogram measures the activity in bipolar cells, cones, maybe amacrine, and they've noticed that the rate of firing changes based on the type of defocus. A couple of our master students are studying this right now. And myopic defocus, when the eye is in that situation, you get more firing out of the ERG studies. When it's in hyperopic defocus, there's less. So when the eye is out of focus, there are a number of methods that are used to compensate. Pupils can constrict or dilate to lengthen or shorten the depth of field. Accommodation can take place to make the lens have more or less power to focus put the point of focus closer or farther away. The choroid thickens or thins. Now the choroid, you'll recall, there's the retina, then there's the choroid, and then there's the sclera. The sclera is kind of like a wall. And when the choroid thickens, it pushes the retina forward, and if the eye is in myopic defocus, the choroid thickening pushes it up there to make that be more in focus. Same way with if it's hyperopic, it thins and lets the eye essentially get a little longer. Now, eye growth is another issue when the eye is by the eye growing longer, becoming prolate, or it doesn't have to be prolate, but as the eye gets longer, then it tends to bring hyperopic images into more focus. One of the things about myopia is that when the eye is round, we call that oblate. When the eye is like a football, we call that prolate. And myopia is when the retina is kind of too far back and the image falls in front. So you wouldn't think the eye would grow under myopia, but the problem is that applies to the central. The evidence suggests that the issue with the eye growing too long is that it's in the periphery. The information used to determine eye growth is in the periphery, and the periphery relative to the central. And so when the periphery, well, for example, if you're a little myopic and you get glasses, then you focus at central, but the aberrations in the periphery make the periphery look hyperopic relative to central, and the eye is tricked into thinking it needs to grow longer. And so when you fix somebody's vision with single vision lenses, their eyes tend to grow more, which kind of defeats the purpose, and you have to keep giving new prescriptions. It's kind of a great job security for optometrists because people need their prescriptions renewed as things get messed up. Okay, let's look at this graph. So let's try and explain this. So we have the back of the eye with the retina and has a certain thickness. Then we have the chromatic spectrum, the visible light spectrum, which the shorter wavelengths are at the front end and longer wavelengths are at the back end. So you're born hyperopic, and as you grow, you tend to have different points in focus. This little curve right here is the strength of the response to the retina, or to the various cells, as they come close to the retina. So if you're in focus, the violet end is just beginning, or it's getting near the peak up here, but red gets very little. And so the eye has said, well, I need to grow a little bit in order to get in the middle here. So it grows a little bit, and now after time, the retina is positioned a little bit further back, and it says, well, I'm doing better, but now I'm starting to get at my peak violet, so I need to slow down my growth a little bit, and so that, but I still don't have any red, and the balance between these two isn't very good. Finally, you get a balance between the blue and the red as each overlaps the retina a little bit. So the peak focus is in green. Now, for some people, the blue is kind of a stop, and they'll stop a little bit in front of that. This guy right down here is a 3 diopter or more hyperope, and he doesn't get any signaling. So the eye doesn't know where it is, so it doesn't know what to do, so it doesn't do anything, and that person stays hyperopic. So if you have a patient who's 3 or more diopters hyperope, they're probably going to be that way forever. So, all right, now what happens? Why does it not work right? Well, as we move indoors and spend more time, in the evolution of people and animals and everybody, we were outdoors a lot, at least half the day, and in the light and sunshine. But inside, there's not much blue light. Indoor lighting is such that the fluorescent lighting in the first year classroom, which sadly we can't experience anymore, doesn't have very much blue light, and so the eye doesn't have this stopper. So it's going along and it's growing and it's growing, and it's not getting enough blue stimulation to ever stop. So it kind of keeps going, looking for that higher blue stimulation, and finally it doesn't get any, the green starts to go down, and the eye says, oh, okay, I don't know what's going on, but all of this red is too much red, and so the eye stops. And there's a couple of interesting studies that have been done. And one of them is a chick study where the animals were raised in a red light environment with a little bit of green, and they just kept growing, and they became very myopic. And then another group, or actually they did a crossover, but another time they're raised in blue light with a little bit of green. And that relative information is what made them grow. And they stopped early and remained hyperopic. Animals raised in only monochrome light, if it was just red, but only red, they stopped right away because they didn't have any blue telling them to go on. And if they were raised in only blue, then they grew to a normal emmetropization, but then stopped growing. So these two studies, this was with tree shrews and this was with chicks, they kind of made the point that it's a relative change that's important. Then there was a long-term study, a longitudinal vision trial, development of myopia, CLEAR trial. And this was a multi-center trial. And what we did was we matched the patients that were ultimately became emmetropes to those that ultimately became myopes. And then we matched them on all kinds of figures. And this was a propensity analysis because you can't randomize kids into being myopes or emmetropes. So we used them where they were. And we looked at effect sizes. We had the parents say what their activities were. And they talked about outdoor activity, how much time did they spend outdoor versus near work, which is things like looking at the computer, reading, studying. And then TV. TV's kind of in between. It's not really near and it's not outside. And of these, only outdoor was significant. And it was near our criterion of a standard deviation size of 0.47. Our criteria is 0.5, and it almost made it in terms of clinical relevance versus the other two that were much, much smaller. There have been several randomized trials in Chinese schools that have demonstrated protection with a modest addition of extra recess, although the effect size was small, and we're going to look at one of those in a minute. So the reason that we suggest that outdoor activity is important is because this is the distribution of light outdoors. And we have all these photons raining down on us. And the peak point is at 480 nanometers, which is at the upper end of blue, just before it goes to green. And we'll talk about this maybe next time on its relationship to circadian rhythm and how that works. But here is our theory of why outdoor light is protective. And I would say that this is something I put together, but it's been put together through consolidating a lot of studies. So what happens is we go outside, our pupils constrict in order to reduce the amount of light coming in because it's so bright. And the depth of field increases. And because sunlight is primarily blue, that it simulates the effect of plus lenses in the periphery. So it's like we're putting on a plus lens, which has been shown to slow the growth of the eye. The S cones are firing much faster. Accommodation kicks in to bring the blue into focus, but it cannot maintain this accommodation over time, and lag increases, and that just exacerbates the problem. The pupils are already constricted, so they can't do any more. So the blue-driven defocus continues to stimulate the amacrine cells. Amacrine cells release dopamine, which diffuses back to the retinal pigment epithelium. Melatonin suppresses dopamine, but melanopsin, which is stimulated by bright light, suppresses this melatonin. And what happens is the border opens where fluid runs out of the RPE and across Brooks membrane and into the choroid, which then sucks it in and thickens. The thick choroid pushes the retina forward to compensate for a myopic shift. But the choroid needs to maintain a homeostasis as well, so it sends a signal to the sclera to stop growing longer so that it doesn't have to keep doing stuff, pushing the retina forward. The eye needs to grow longer. And so this may change the eye to be a little more oblate, spherical. The action of the sunlight prevents the spherical and peripheral curves as well. This is something we didn't cover, but what that is referring to is it keeps the relative refractive error from going between peripheral and central, from hyperopia being hyperopic, the peripheral being hyperopic to central, and myopia is prevented. One thing is there's no evidence suggests that once you are myopic, playing outdoors is going to help you. It prevents that crossover from myopic refractive error to hyperopic refractive error relative to the central. All right, so that's that I wanted to discuss. And I'm going through these papers. We did one last week on risk, and I'd like to go through this paper in a similar way because I think it can, well, for one thing, in our final, we're going to have examples like this, present a paper, and we'll ask questions. So we're going to go through and see some of the types of questions that will be asked. And so this is a title that was done in China, Effective Time Spent Outdoors at School on the Development of Myopia Among Children in China. It's a randomized clinical trial. And here are the authors. It talks about importance. Myopia has reached epidemic levels. There's no effective intervention to prevent the development of myopia. And so the objective of this study was to assess the efficacy of increasing time spent outdoors at school in preventing myopia. So the question is, what type of design do we have here? And it's a cluster randomized trial. Now, why is it called a cluster? It's a cluster because they look at, they randomly select schools, but in the school they look at all the children. So all the children in a school are a cluster. And they're first graders, and there were 6 schools that received the intervention, 952 students. And the control schools were 951 students, 6 schools there too. So that's a pretty big study. It's clustered, which makes the effective N a little bit smaller actually. But what was the intervention? It was an additional 40-minute class of outdoor activity added to each school day. And parents were encouraged to engage their children in outdoor activities after school hours, especially during weekends and holidays. So do you think a 40-minute class is sufficient? I don't know. It's not a very big, dramatic intervention. But, we'll see what happens. So the main outcome measures, the primary outcome measure was the 3-year cumulative incident rate of myopia. It's like we talked about last week. And they defined refractive error as minus 0.5 diopters. The secondary outcome measure was change in spherical equivalent refraction and axial length among all students. And they used an intention to treat principle. Intention to treat is if someone drops out, then they get, or potentially moves to another school, they're counted with as much data as they have in the first school. Now, in this study, they only used data from the right eyes, which is also the same as they did in the CLEAR study. And the reason they only look at right eyes and not both eyes, is because eyes are not independent observations. One of the requirements we have is for independent observations. So, what were the results? The cumulative incident rate of myopia was 30.4% in the intervention group and 39.5% in the other group. Now, a question is, now they did a difference of 9%. We usually prefer to think of relative risk. So what would be the relative risk? How would you formulate the relative risk in this study? Now, remember, control groups are usually used as the reference. So where would the control group go? In the numerator or the denominator? They would go in the denominator. And the intervention would go in the numerator, and so we would take 0.3 over 0.39, and we would have a relative risk of about, that's around 30 over 40, or about 0.75. So from a relative risk point of view, this study was protective. They did their confidence interval on this difference of 9.1% and showed that the confidence interval went from minus 14 to minus 41. Now, in a relative risk, what is the null hypothesis? Is it 0? Is the intervention risk over the control risk? Does that have to be 0 to be a null hypothesis? No. The null hypothesis is 1. There's no difference, it's 1. And so it moved away from relative risk to from the null hypothesis to 0.75. In their confidence interval, they did a difference. Now, this is more of so what is in the difference? What is the confidence interval? Or what is the null hypothesis? The null hypothesis of a difference is 0. So if they were both the same, if their proportions were both the same, the difference would be 0. So the null hypothesis and what is the same or different depends on the type of test you're doing. If you're doing a relative risk, the null hypothesis is 1. If you're looking at the difference between groups, the null hypothesis is 0. And the probability of finding the statistic, which they don't list here, but it's probably a z-test. The probability of finding a z with this much difference is very small. That's what that p means. It's very small. And what we would want to do is look at effect size. Now, again, as I said, we're looking at relative risk, and a 25% drop, 1 minus 0.75, pretty big drop. And that would affect a lot of children given the incident cases that we have here. Then let's look at another way of doing this, and that was that they had, there was a significant difference in spherical refraction for the intervention group. The change was minus 1.42 compared with a 1.59. And that's a difference of 0.17. And their confidence interval was 0.01 to 0.33. Now let's take a look at this one, and we could have done this up here as well. But this is significant, not highly significant at 0.04, but it's significant because the confidence interval does not overlap 0. The confidence here does not overlap 0. If it overlapped 0, it wouldn't be significant. But it's pretty close to 0 at 0.01, which is why the p is only 0.04. They also looked at elongation of axial length, and that was not significantly different between the intervention groups. And in this case, we see the confidence interval is minus 0.07 to plus 0.003. And so that overlaps 0 and is not significant. Okay, so what do they conclude? Among 6-year-old children in Guangzhou, the addition of 40 minutes of outdoor activity in school compared with usual activity resulted in a reduced incident rate of myopia over the next 3 years. So that's the abstract. Now let's take a look at some of the figures. And one, let's see, where are we? We're in, this is the, okay. So the first figure is just the design. And they went out and they looked to see which schools documented or had documented annual visit acuity data. And so they had 12 schools that were selected, and they randomized them, and so forth. What were the results? Let's look at Table 1. Mostly papers with Table 1 look at baseline characteristics. Now, if we look down here, we see that we had a p-value of 0.01, but really those ages aren't all that much difference. Then everything else was not really significant. It might have been axial length was a little longer to start with in the control group. This is control on the right. But down here, this was somewhat troubling. This was a difference at baseline in parental myopia. There's a lot of evidence showing that if your parents are myopic, you're going to be myopic. And you can see there were, in the control group, there were fewer, 40% versus 46%, fewer kids whose parents had no myopia. So you would expect these kids to to have more myopia, basically. And the same way with one parent and two parents. So 23%, both parents were myopic. You'd expect the control group to be more myopic. And that's actually what they found. Now, this is the cumulative incidence of myopia, 30 versus 39. The difference, the p-value, and these are the changes. That's just talking about the data we had before. And this looks at the time spent outdoors at baseline and follow-up. And notice these numbers are very close to the same. That's because they don't add in the 40 minutes. This is just asking the kids how much time they spent outside in the program. So the instructions telling the parents to encourage outdoor activity after school on the weekends didn't really do too much. I mean, there's slightly higher numbers there, but you can see the p-values weren't rejecting in chance. I wanted to point out something that was disturbing to me was the difference in the parents. And what they did, and they did a post hoc logistic regression model adjusting for parental myopia. So what that did was they statistically made everybody the same. And in this case, they got an odds ratio from that of 0.73. They used logistic regression, and logistic regression gives you odds ratios rather than relative risk. And you'll remember that we have said that the odds ratio makes things look a little bit better than relative risk. And we were 0.75 with relative risk, we're 0.73 with this, but it's still significant. So after adjusting for that difference in parental myopia, they still found an effect of the outdoor activity. And that's pretty impressive. And so that's all the papers. But I think what we want to do now is let's take a look at these values. Now, let's get a spreadsheet up. 1 second here. So here I've laid out an Excel sheet to kind of clarify our calculation of effect size. We're taking the data from this table up here, which talks about spherical equivalence, spherical equivalent refraction in diopters. Intervention group is a mean of minus 1.42. Control group, a mean of minus 1.59 down here. And then a lower confidence interval of minus 1.58 to minus 1.27. And for the control, it's minus 1.76 to minus 1.43. Now, if you will recall, this is a 95% confidence interval. So that means that 95% of our variability here is within plus or minus two standard errors. So to estimate what a single standard error is, we divide by 4, because 2 plus 2 standard errors plus 2 standard errors, 2 plus 2 is 4. So we take the range, we divide by 4. So it's the absolute value, because we want our range in we don't want any minuses in here. So we have minus 1.27 minus a minus 1.58. And then we divide that by 4. And it gives us a standard error of 0.0775. Now, to compute effect size, we need the standard deviation. So there's an n of 919. And when we know the standard error, the standard deviation is the standard error, which is E20775, times the square root of n, which is 919. And that ends up with 2.35. Now, if you're getting lost in this, which you very well may be, then I suggest going over the standard deviation video and briefs earlier in the semester. It's a long time since then, but that's where we get this. Now, to compute effect size, it's the difference between means divided by the average standard deviation. Now, let's just for the heck of it go through how we calculated this 2.51. So, it's the lower confidence interval is minus 1.76 minus 1.43, and that range is 95% of the theoretical means fall in there. It's not exactly that, but they fall in there. We're estimating this is plus or minus 2 standard errors, and so it's 2 standard errors to get to the minus 1 from the mean, minus 2 standard errors to get here, and the mean plus 2 standard errors to get here. These are smaller numbers because we're dealing in negatives. And then we get that difference. We divide by 4. So it's the difference of those two divided by 4 gives us the value of 1 standard error. And the standard deviation is the standard error times the square root of n. And that is this range divided by 4, the standard error, times the square root of that gives us a value of 2.51. The average of these two is 2.43. It would be nice if people would always write articles where you get the standard deviation. The problem is that doesn't happen very often. So or it happens, but not when it doesn't, you have to calculate it. And I'm sorry that this is complicated, but it's getting you to the point where you can determine the clinical relevance in terms of this. And if we look at the average standard deviation and the mean difference divided by that, you get an effect size of 0.07. Now, what is our rule of thumb for a clinically relevant effect size? It's 0.5. And a very small amount is 0.2, and trivial is less than 0.2. So this is much like our PAL SBL study that we looked at earlier. Did progressive addition lenses help in slowing down myopia? And they were significantly different, mostly because there was a big N then. Well, there's a really big N here as well. And so we're finding this 0.04. But with an N of that size, a P of only 0.04 leads you to expect a very small effect size like this. So the study authors have suggested that outdoor activity may be affected. Now, we didn't do the effect size for the incidence of myopia. And believe it or not, from the data that they gave us, we could calculate it, but it gets even more complicated because they gave us the confidence interval of the difference, which is not the same as the confidence interval for each of these things. So I don't want to screw up your brains any more than I already have. And we're just going to say, 0.75 is not bad. So while they conclude that it might make a difference, my conclusion from this is yes, outdoor activity and sunlight may be a protective effect, but 40 minutes added each day is probably not enough to have a significant effect. And they were not able to show that the parents encouraged their kids to go out more, and just 40 minutes is just a trivial amount, and it didn't work out too well. So this is looking at effect size in this case, and I hope that you don't get lost too much. If you have questions after reviewing the standard deviation and how you can estimate effect size, just let me know. I have office hours at 4 o'clock on Mondays for the next 2 weeks. All right, that's it.